everyone, and welcome back to my channel. It's been a while since I've done my previous video, and I hope you will really enjoy this one that I've just finished. I had a lot of university stuff to do in the meantime, so I finally found some time to make a third video. However, this video is going to be very specific for mathematical calculations, so it's going to be very heavy on maths. And if your math knowledge is not that deep, like we're talking about high school level, it might be hard for you to follow this. But if you want, you can try, obviously. I mean, there's always opportunity to learn more things, but it might be too much of a jump for you. In case you have university level math, this could be interesting to you, but this is obviously related to top drives. So we start with this potentially useful concept for acceleration curve in the game, and I start to talk about the systematic solution. So the systematic assumption is basically the differential equation. Differential equation is basically what you see here in the slide. dv over dt equals k times a minus v, where dv over dt is known as acceleration, k is the scaling factor. You will find out that a is top speed, but for now it's just a general constant, although it is the top speed, and v is the velocity or the speed that the car is at a given time t. So this differential equation is a systematic assumption to the acceleration curve of a car. So the simplest case for a smooth acceleration of a car is given by this equation. And now we kind of move on from this, and we want to solve for the specific values of this differential equation, because we don't know the acceleration is technically what we want to find. But we do know the velocity and the time at which the velocity is obviously given in the game, and therefore we want to solve for the velocity in the first place. And then we will solve for the k factor, which is what we're interested in afterwards, but for now we just solve for the velocity. And we can use the method of separation of variables. So does this mean that you can bring all the values that include v on one side and all the values that include the t on the other side, and we let a u equals a minus v in order to solve this really simple integral, which then gives you du is equal to minus dv. And then we solve the integral, which is a known integral, and this is the logarithm as a result. So you will get negative log of u equals kt plus a constant, which we will call c1, which is a constant of integration. Then we can just solve for this value of u, which we know to be a minus v. And we will find in the end, after all these procedures, that a minus v is equals to e to the power of minus kt times e to the minus c1, which then we will call c2. And then we solve this, and you get the final result to be v of t, so this is your velocity equation, is equals to a minus c2 times e to the negative kt. Now we will also want to find the value of c2, and we can do this by knowing the initial condition. So without an initial condition, we wouldn't be able to find this. But since we do know it at time 0, our car is stationary, so velocity is also 0. This is our initial condition. And so we can apply that for v0, you get 0, and you can apply for the time 0. You know that the exponential to the power of 0 equals 1. So you get as a result a minus c2, which means that c2 is equals to a, which then the overall equation turns out to be a times 1 minus e to the power of negative kt, which is the general solution to this differential equation. From this, we can actually find the value of k, because that's what we're interested in. And you can read it in this slide that we know the velocity, the speed, we know the time, we know the top speed, and so we want a general k factor which would allow us to predict the speed, the velocity, and so the speed and the time at any point in the acceleration curve. So if we find a constant value that is consistent, so we prove that this k value is consistent for a given car, then you can just replace that value into your differential equation and find all the values that you need. So, but first we need to prove this, right? So we need to find if this is consistent. So I took, first I rearranged the formula, right, in order to fulfill, to make everything dependent on k, right? So we want to find k, so we want to find values that would fulfill this k value. And I took two cars. The first car is the Dodge Challenger SRT Hellcat Red Eye Wide Body Jailbreak. I know it's a long name. And also something very important to point out is that I have used this car's stock because that's the truthful acceleration curve of the car. Otherwise, we get some random variables. We don't really know what's going on when upgrading the car. So we first want to find the simplest case, which is when the car is stock, and then we may develop afterwards when you have upgrades on it. But I first found I took some times for a drag race, and I also took the speed at that time. So those are a screenshot I have. I didn't post it here. I didn't put the video on it, but it's I guess it's a trust me, bro, kind of thing. These are the values that I found, and I converted them into SI units because I don't like to work with miles per hour. It's just very inconvenient, I would say. And I found some values, and this is very interesting because we already can tell that k isn't constant. Okay, there may be some error, but the error seems very big. So this can't be. K isn't constant. But nonetheless, we may want to see a certain trend. So if the same trend appears for the next car, which is the Cadillac CTS Sport Wagon, if we see the same pattern, then we can conclude that there must be an equation that fulfills the value of k. However, when seeing the values of the Cadillac, the k factor is always decreasing over time, which is very particular. But that's why we do this. Like, this is the initial hypothesis, is that the function would have a constant k factor, but that doesn't seem to be the case. And if since we observed these equations, we observed these values, basically we can kind of understand how they behave, at least with the given values that I took. And I would assume that the function is relatively smooth at the very least. However, this still indicates some, or implies some conditions. First of all, the k factor is not constant. That's what we already said. And so it may vary with time. And the k factor is not monotonic. And that can be the reason if we look at the Dodge Challenger SRT Hellcat Red Eye White Body jailbreak, that basically it's a paraboloid curve. The trend that the k factor is following is a paraboloid. Meanwhile, for the CTS Portwagon is an exponential decay. An exponential decay is monotonic, but the paraboloid is not following the same trend, and it may not be monotonic. That's the idea. So could be a mistake, but I'm pretty sure that the curve isn't monotonic. The k factor may not be a single variable function, so it could vary with time, but it could vary also with other variables that we don't know, which would be interesting to know because it's quite peculiar, I would say, if it doesn't change with time. But there could be also another case for which the k factor may be a piecewise function, and in that case it's very hard to determine, because a piecewise function means that basically the curve accelerates in a certain way at a certain given time, and then it changes. The rate kind of suddenly changes, and that's the piecewise function. But in theory, it should both fulfill the continuous and smooth function in theory, but I'm not that sure about it. So we keep on going, and I actually find this as the most possible consideration for k. So I first determine that k only depends on time, and maybe it works, maybe it doesn't, we don't know. But still, we want to solve this differential equation, which looks like the same as the one that we started with, which technically is the same, just that now k depends on time. And because of this, the computation is much harder, only because of dependence, because now it becomes a function and it's not a constant anymore. So in order to solve this, we make a substitution. We let u of t to be k of t times a minus v of t. All of the variables aside from a is a constant, all the variables are dependent on t. We apply the derivative with respect to t, and we find this condition here. And we want to solve for dv over dt, which is the term that is multiplied by k of t. And we want to solve for that because then we can replace it back to the initial equation that we had, and we can solve for u and k instead of basically free functions, which is dv over dt, k and v. That k is very inconvenient there. So we want to have u and k to solve for. And we do some computational math that, if you want, you can check yourself. I'm probably have done a mistake or not. Who knows? I mean, you can check. I'm pretty confident on what I did. So this is the procedure. We then replace everything. When we found dv over dt, we replace it back to the original equation. And we know that the right hand side is equal to just to u of t, right? So that's a cool condition. Then we bring k of t on the other side, and we multiply both, so right hand side and left hand side, by k of t. So we can expand in the bracket, and we know that k of t times a minus v of t is again u of t. So we replace it back there, and you have this condition here. We want to solve for du dt, which is what we do here, which du dt equals 1 over k of t times u of t times dk over dt minus k of t times ut. Again, this is a separable differential equation, which we can do. We can bring u on one side, and so the u on one side remains, and you bring dt on the other side. We know that dk over dt times dt times, integrated by dt is just dk. So we just have the resultant of the integral on the left side, which is a logarithm of u of t, is equals to the integral of 1 over k dk minus the integral of k of t dt. Since we can't solve the integral of k of t dt because we don't know what k of t is, we can only solve the first term on the right hand side. And so we have logarithm of u of t equals logarithm of k of t minus the integral of k of t dt. We expand again, so we knew that the definition of u of t is just k of t times a minus b of t. We replace that back, and we use the properties of logarithm. So if the inner argument is multiplicative, then it's the sum of the logs. And that's what you do. You have log of k of t plus log of a minus v of t equals log of k of t minus the integral of k of t dt. And indeed, the log of k of t just cancels us out. And so you have an equation that is dependent on a minus v of t, which is e to the power of the negative integral of kt dt. We replace this then into the original equation, for which we have dv over dt equals k of t times e to the negative integral of k of t dt. We make a very interesting substitution, which is v of t, w of t actually, because I say v in my language, but it's w of t, is equals to the integral of k of t dt. From this substitution, we have dv over dt equals k of t times e to the negative wt of t. However, we want everything in the w world. Okay, so we don't want that k. That k is very nasty because we just changed the variable. So we want to define this in terms of dw. And that's what we actually do. We know that dw is equals to k of t dt because that's the initial definition. Basically, w of t is actually the integral of dw, because that's what you get. It's a variable that you kind of obtain from the integral of the variable itself, right? So we can rearrange in terms of dt this time, and we have dw over k of t, which means that we divide by k of t, and so that terms disappears, which is really convenient. Now, we apply the integral on both sides, and you get vt, so v of t, equals the negative e to the negative w of t plus a constant c. You replace back the definition of w of t, and you get that v of t is equals to the negative e to the negative integral kt dt plus c. Which was tough. This is the general solution for the differential equation for an arbitrary function k of t. However, in the examples that we've seen, the function k of t could take the form of a monotonic function as well as a non-monotonic one. My assumption is that since for the Dodge the value k of t was sort of a paraboloid, so it's a parabolic function, my assumption is that this function here is the hyperbolic cosine. I might be wrong, but this is my from the observation of the values, I think that this is an hyperbolic cosine, which is defined in the following way, as you can see on the slide. While for the Cadillac, k of t may take a decaying exponential form, which is the following function that you can see on the slide. If k of t is actually the function in question, so if that's it, so k is of t, it cannot change its form. It cannot be one equation and another equation. It's just one. It's just one function. And any value of t needs to fulfill that function. Unless you define it in a different way, which is a function of a function. So as that function varies with time, k varies with the function which varies with time. But also this definition may not fulfill the differential equation as a whole. So it may be that you need an additional function inside of the function, and this could technically go to infinity if you can't find a fulfilling equation to this differential equation. However, we can actually go from one equation to another that have a very similar form, and we can define this function to be the following. So we define k of t to be this e on subscript alpha beta, which then I will get to it, of g of t. G of t is a function that can be found experimentally only in relation to this function, which is called the Mittag-Leffler function. This function actually intertwines other functions, very like elementary functions as well, which have a very similar infinite sum when you expand them as an infinite sum. And thus its definition is given in our last slide, which it's this sum here. And alpha and beta are just variables. Technically, beta will always stay to 1 if the functions are very, very easy to determine. beta generally stays at 1, and you have kind of the reduced Mittag-Leffler function. But otherwise, it's better to define it with beta. There's also a gamma term, that's the extended Mittag-Leffler function, but I don't think that's the case for this situation. We could also look at it if it's even more complicated than what it looks like. But then you can notice in this expansion that in the denominator there is a term which is called the gamma function. And the gamma function, for those who do maybe engineering, for those who do like maths and physics, this function appears very often. And this is basically the extension of the factorial. And so you know that the factorial is like n factorial is like n times n minus 1 times n minus 2 blah 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 till 1. So this is the extended function. So a function that is extended to the domain of complex numbers. So the factorial is just for natural numbers, so for 1, 2, 3, 4, 5, and so on. While the gamma function includes all the complex values. Okay, so real, imaginary, rational, whatever. I mean, rational is a subset of real, and real is a subset of complex. So there you go. So if my assumption that the two curves defined previously, so the hyperbolic cosine and exponential decay function, turned out to be correct, we can actually write those two functions with the g of t equals negative lambda t. Lambda is just a factor, is kind of the new k factor. And we can define this in generic Mittag-Leffler function, because the two functions there, the two expansion of the two functions, are very similar. You need to change some values, so that generally you need to change the value of alpha in order to change from one value to the other. But we can technically write this k of t with this Mittag-Leffler function, and I think that this definition is a pretty good starting point to find a generic form for every car in the game. Although you may need to find a particular value of alpha for every car, and that may take a lot of time. But I think this is a very good starting point, and I think we can predict the speed for every car in a straight line just by using this final function. And the value of c you can actually find whenever you know the equation that is governing the acceleration curve. So whenever you find the generic Mittag-Leffler function of your car, then we can apply the initial condition for which the velocity at time 0 is 0. So let's say that the exponential, the Mittag-Leffler function is outputting an exponential function. So you can do that 0 is equals to negative e to the power of negative 0 dt. So it means it's a e to the power of negative constant. And that's basically your c value. The c value, you just rearrange it. Okay, this is just an example, but I wouldn't go in detail without knowing the generic function g of t. And indeed, we actually need experimental results in order to determine this. Hi there, back, and I hope you enjoyed this video. I'm sorry that I kind of moved on. As you can see from the background, is not the same. I had to, because I'm a bit busy and I'm moving a bit back and forth, and then soon I will be going back to my country. So I'm recording from a different place, but I I really hope that you enjoyed this video, and let me know in the comments if you liked it. You did not. I think most of you probably wouldn't like it. It's very specific, and I hope you have a nice day, and also happy Christmas, happy New Year, in case we don't hear each other again. And in case you want to chat with me, I'm always on Discord, or relatively active on Discord, on the TDO server, as always. And see you. Goodbye.